Block 1. The Mind Behind the Atom's Secret. Welcome, science enthusiasts and history buffs. Today, we're peeling back the layers of history to uncover one of the most significant yet tragically overlooked stories in the annals of physics, the extraordinary life and monumental discoveries of Lise Meitner. Often hailed as the German Marie Curie, Meitner was an Austrian-Swedish physicist whose brilliance didn't just illuminate the structure of the atom, it fundamentally reshaped our understanding of the universe itself. Her journey is a compelling tapestry woven with threads of groundbreaking scientific inquiry, immense personal sacrifice, and a profound historical injustice that continues to resonate even today. Born in 1878 in Vienna, Austria, Lise Meitner, later known as Lise, faced an uphill battle from the very beginning, simply by virtue of her gender. In late 19th century Austria, women were largely barred from higher education. Yet, Lise's insatiable curiosity and formidable intellect could not be contained. She tutored privately to pass the exam, a rigorous university entrance qualification, a feat she accomplished at the age of 23, remarkably late for aspiring university students, but a testament to her determination against systemic barriers. Imagine the sheer willpower required to self-educate to that level, overcoming societal expectations and institutional discrimination. This early struggle forged a resilience that would define her entire career. Her perseverance paid off when she finally entered the University of Vienna in 1901, where she studied physics under the legendary Ludwig Boltzmann. Boltzmann was a profound influence, igniting her passion for theoretical physics and the intricate dance of atoms. His lectures, reportedly, were so captivating that Meitner herself described them as beautiful and stimulating. This period was formative, grounding her in the cutting edge of physics and preparing her for the revolutionary work that lay ahead. After earning her doctorate in 1905, only the second woman to do so in physics from the University of Vienna, she moved to Berlin in 1907. This move marked the beginning of her pivotal collaboration with Otto Hahn, a chemist, at the Kaiser Wilhelm Institute for Chemistry. Their partnership was, for decades, a symbiotic relationship. Hahn, with his meticulous experimental skills, and Meitner, with her unparalleled theoretical insight and understanding of the underlying physics, formed a formidable duo. Initially, due to the prevailing sexism, Meitner was not even allowed to work in the main laboratories. She had to conduct her experiments in a converted carpenter's workshop in the basement, and even enter through the back door. She received no salary for years. This was the stark reality for many pioneering women in science, their genius often relegated to the shadows. Despite these indignities, their research flourished. They delved deep into the nascent field of radioactivity, discovering new isotopes and unraveling the complex decay chains of heavy elements. Their focus was on understanding the behavior of uranium and other heavy elements when bombarded with neutrons, a field that was rapidly evolving thanks to the work of scientists like Enrico Fermi. The intellectual climate of the 1930s was electric with discoveries about the atom's nucleus. Scientists worldwide were experimenting with bombarding uranium with neutrons, hoping to create new, heavier elements known as transuranic elements. Hahn and Meitner, along with Hahn's assistant Fritz Strassmann, were at the forefront of this research. They meticulously performed experiments, observing strange and perplexing results. When they bombarded uranium, they expected to find elements close to uranium on the periodic table, or perhaps entirely new, heavier ones. Instead, they began detecting lighter elements like barium. These findings were utterly baffling, defying all known laws of nuclear physics at the time. How could a heavy uranium nucleus, when hit by a tiny neutron, break apart into much lighter elements? It was like hitting a bowling ball with a ping pong ball and having the bowling ball split into two small marbles. The experimental evidence was there, undeniable, yet the theoretical framework to explain it was missing. This was the precarious state of science just as the political landscape in Germany turned terrifyingly dark. As an Austrian Jew, Lise Meitner's position in Nazi Germany became increasingly perilous. Despite her international scientific renown and her initial protection as an Austrian citizen, the annexation of Austria by Germany in March 1938, the Reich, stripped her of this safety net. Her colleagues, including Hahn, grew increasingly concerned for her safety. The danger was palpable. In July 1938, with literally just a few marks in her pocket and without her cherished research notes, she was forced to flee Germany in a clandestine escape, helped by Dutch physicists Dirk Koster and Adriaan Fokker, eventually making her way to Sweden. This hasty, desperate exodus left her isolated, without proper laboratory facilities, and emotionally drained. Yet, even from exile, her mind remained acutely focused on the puzzling experimental results that Hahn and Strassmann continued to send her. It was during this period, through intense correspondence with Hahn, that her theoretical genius truly provided the definitive explanation for their experimental results. Hahn wrote to her, desperate for an explanation for the barium mystery. Meitner, along with her nephew, physicist Otto Robert Frisch, would soon provide the answer that forever changed our understanding of energy and matter. They realized that the uranium nucleus wasn't simply undergoing a slight alteration. It was splitting apart, a process they termed nuclear fission.
Fission, nuclear fission. This was not just a new reaction, it was a paradigm shift, unlocking the immense energy bound within the atom's core. The implications were staggering, paving the way for both unimaginable destructive power and the promise of a new energy source. Prepare to delve deeper into this incredible discovery, the personal sacrifices it demanded, and the enduring historical injustice that still resonates today. Block 2. The Breakthrough and the Betrayal. The intellectual tension mounted in late 1938. Otto Hahn, still in Berlin, was bewildered by his experimental results. He had consistently found barium, a much lighter element, after bombarding uranium with neutrons. He wrote to Lise Meitner, his longtime collaborator, expressing his profound confusion. Perhaps you can suggest some fantastic explanation. We know that it cannot burst apart into barium. So please think. If there is anything, you will surely find a way out. Hahn, the meticulous experimentalist, recognized the anomaly but could not reconcile it with existing nuclear physics. The prevailing scientific wisdom dictated that nuclei were incredibly stable and only tiny fragments, like alpha particles, could be chipped off. Splitting a heavy nucleus into two roughly equal halves was considered impossible, almost absurd. It was during her Christmas holiday in Kungälv, Sweden, that the answer struck Lise Meitner. She was with her nephew, Otto Robert Frisch, a brilliant young physicist who had also fled Germany. As they walked through the snowy landscape, discussing Hahn's perplexing findings, an idea began to coalesce. Frisch later recounted their discussion. It was a cold day, and we walked through the snow, Meitner and I. I was trying to explain to her that the uranium nucleus could not possibly split, but she kept insisting that it must have. Meitner, with her deep theoretical understanding of nuclear structure and the concept of liquid drop model of the nucleus, realized that a heavy nucleus, like uranium, could indeed behave like a large, unstable droplet of liquid. If hit with enough energy, it could oscillate, elongate, and then split into two smaller droplets. The true stroke of genius came when Meitner applied Albert Einstein's famous equation, E equals mc squared. She calculated the immense energy released by this splitting process. Comparing the mass of the uranium nucleus before the split to the combined mass of the barium and krypton nuclei after the split, she found a significant mass defect. This missing mass, she realized, was converted into an enormous amount of energy, precisely as predicted by Einstein's equation. The numbers added up perfectly. About 200 mega-electron volts of energy per fission event, an unprecedented amount for a single atomic reaction.
This was the moment of revelation. The uranium nucleus wasn't just reacting, it was literally splitting into two lighter elements, releasing a colossal burst of energy. Frisch coined the term nuclear fission for this entirely new nuclear process, borrowing the biological term for cell division. Hahn and Strassmann published their experimental findings in January 1939, acknowledging Meitner's earlier input, but, understandably given the political climate, omitting her name from the authorship of the paper itself. Just a month later, in February 1939, Meitner and Frisch published their seminal theoretical explanation of fission in the journal Acton, titled Disintegration of Uranium by Neutrons, a New Type of Nuclear Reaction. Their paper provided the crucial physical interpretation, transforming baffling experimental data into a profound scientific breakthrough. The scientific community was electrifyingly quick to grasp the implications. Within weeks, laboratories around the world were replicating the experiment and confirming the colossal energy release. The realization that a chain reaction might be possible, where the fission of one uranium atom could release neutrons that would then trigger further fissions, immediately sparked both excitement and apprehension. This discovery occurred on the precipice of World War II, and its potential military applications were not lost on anyone. The ability to unlock such immense energy hinted at weapons of unimaginable power. Meitner, a pacifist, was deeply disturbed by this prospect. She famously refused invitations to work on the Manhattan Project, stating, "I will have nothing to do with the bomb." Her moral compass was unswerving, even as the world around her descended into chaos. As the war ended and the world began to pick up the pieces, the scientific community turned its attention to recognizing the monumental discoveries made during those tumultuous years. In 1944, the Nobel Prize in Chemistry was awarded solely to Otto Hahn for his discovery of the fission of heavy nuclei. The omission of Lise Meitner was and remains one of the most glaring injustices in the history of the Nobel Prize. Despite her pivotal role, providing the theoretical framework, the physical explanation, and the term fission itself, her contribution was sidelined. The reasons for this exclusion are complex and multifaceted. The political climate of the time certainly played a role. Meitner was an exiled Jewish woman, while Hahn remained in Germany. There were also personal tensions and perhaps a desire by some Nobel Committee members to downplay the theoretical aspects in favor of the experimental discovery. Furthermore, the committee might have been influenced by a lack of understanding of the collaborative nature of the discovery, or perhaps even a deliberate downplaying of her contribution due to personal biases, especially from individuals like Mane Siegbahn, the director of the Nobel Institute for Physics, who held significant sway and harbored a known prejudice against Meitner. This was not merely an oversight. It was a profound denial of her intellectual ownership over the explanation of one of the 20th century's most impactful discoveries. While Hahn himself acknowledged Meitner's crucial role in private correspondence and later in his autobiography, his public statements at the time of the Nobel Prize were often ambiguous, failing to equivocally champion her co-discovery. This monumental injustice left the mother of the atomic bomb, a term she disliked, precisely because she wanted nothing to do with its destructive application, without the recognition she so rightfully deserved. Block 3. Legacy Beyond the Laurels. Despite the profound injustice of the Nobel omission, Lise Meitner's scientific journey did not end in 1944. She continued her invaluable research in Sweden, primarily at the Royal Institute of Technology and later at the Nobel Institute for Physics. Though she often struggled with inadequate resources and a less than welcoming scientific environment, particularly under Mane Siegbahn, her focus shifted from the immediate implications of fission to broader questions of nuclear physics, contributing to fundamental understanding of the atomic nucleus and its properties. While she never received the Nobel Prize, her brilliance was not entirely unrecognized by the wider scientific community.
She received numerous other accolades, including the Max Planck Medal in 1949, the Enrico Fermi Award in 1966, and was nominated for the Nobel Prize multiple times after 1944, a staggering 29 times in total across both physics and chemistry. These nominations, while ultimately unsuccessful, underscore the respect and recognition she commanded among her peers, even if the Nobel Committee failed to acknowledge her foundational contribution to fission. Meitner remained a staunch advocate for the peaceful use of atomic energy and was deeply troubled by the development and use of nuclear weapons. She often expressed her regret that her discovery had been weaponized, stating, "I have nothing to do with the atom bomb." Her moral stance was unwavering. She saw the potential for nuclear power to provide clean energy, but only if handled with extreme caution and ethical responsibility. She continued to give lectures, inspiring new generations of scientists, particularly women, to pursue careers in physics. Her personal integrity and commitment to truth were as strong as her scientific acumen. She retired in 1960 and moved to Cambridge, England, to be closer to her nephew Otto Robert Frisch, where she remained active in scientific discussions until her death in 1968, just a few days before her 90th birthday. The legacy of nuclear fission, born from Meitner's theoretical insight, is undeniably one of the most transformative scientific breakthroughs of the 20th century. It led directly to the development of nuclear power, providing a powerful, albeit controversial, source of electricity that today supplies a significant portion of the world's energy needs. It also paved the way for medical advancements, such as diagnostic imaging and radiation therapy, utilizing radioactive isotopes produced in nuclear reactors. But perhaps most famously and tragically, it provided the scientific basis for the atomic bomb, forever altering the landscape of global geopolitics and warfare. Meitner's discovery stands as a stark reminder of science's dual potential to create and to destroy. Lise Meitner's story serves as a powerful testament to the enduring challenges faced by women in science throughout history. Her experiences highlight not only the systemic barriers, from lack of access to education and facilities to unpaid labor, but also the insidious nature of intellectual appropriation and the biases that can influence even the most prestigious scientific awards. While the 1944 Nobel Prize decision cannot be undone, Meitner's rightful place in scientific history has been increasingly recognized over time. Element 109, a synthetic radioactive element, was officially named Meitnerium in her honor in 1997, a fitting tribute to a physicist who truly understood the heart of the atom. She is now widely acknowledged as the Mother of Nuclear Fission, a title that rightly credits her profound contribution. Her story compels us to look beyond the headlines and official accolades to understand the complex human narratives behind scientific progress. It's a story about persistence against incredible odds, intellectual brilliance that transcends borders, and the often unseen struggles that shape the course of discovery. Lise Meitner's genius was undeniable, even if her accolades were not. Her unwavering commitment to science, her moral fortitude in the face of immense pressure, and her pivotal role in one of humanity's most significant discoveries should inspire us all to champion unsung heroes and to critically analyze the narratives of history. It is a vital reminder that true scientific progress is often the result of collaborative effort, and that recognition should always be based on merit, not on politics or prejudice. Her legacy pushes us to ask, how many other brilliant minds have been overlooked or marginalized in the annals of history, simply because of their gender, race, or circumstances? What do you think is the most significant takeaway from Lise Meitner's incredible journey? Her scientific genius, her moral courage, or the historical injustice she faced? Write your thoughts in the comments below. Subscribe to learn more, and see you soon.